Hello, hello, hello. Okay, let's do some math today. It's for this math time. Yeah, all right. We're doing day 2 of U substitution today. I got a little warm up here. And for once, I'm actually going to do the warm up in the video, okay? Especially number 1. Number 1 is something you could probably do on your own, but something I wanted to talk about in terms of intervals, okay? So it's a particle in motion question. It says we have a particle moving right and left. It has an acceleration modeled by 4t minus 5 feet per second squared. So this is a different setup. Usually I'm giving you s of t and you have to work your way down to a of t. Now I'm giving you a of t and you're having to work yourself backwards. So that's integrals, right? Okay. So I want us to do the velocity function if v of 0 equals 3. So if I'm given a of t, v of t is just the integral of a of t, right? So if I were to integrate 4t minus 5, 4t integrates to, if I add 1 to the power, it's squared, and divide, it's 2t squared. And 5 integrates to 5t. And if I'm finding a generic equation, you have that plus c, okay? Now, normally we would not be able to find out what that c is, but if we're given an initial condition or a point for velocity, I can actually solve for that c value, okay? So if you're asked to work backwards, if you're asked to integrate, and they give you an initial condition, then you can use that to solve for c. Simply put, I just got to plug 0 into that, so that's so v of 0 equals 2 times 0 squared minus 5 times 0 plus c, and it equals 3. And I think everything cancels but the c, so c equals 3. So my equation in this case, v of t, is 2t squared minus 5t plus 3. Boom. All right, so pretty straightforward. Now then B says find the displacement function. So that's the, or position function, which we call S, right? And it wants us to find that given the fact that S of 0 is 5. So we got our V of t equation. If I want to know my S of t equation, I simply integrate. So 2t squared integrates to 2/3 t cubed. 5t integrates to 5/2 t squared, and 3 integrates to 3t. And then I have the plus c. But if I plug in 0 for t, just like in part A, everything cancels, so it equals 5. So in this case, c actually equals 5. Plugging 0 in, setting it equal to 5, makes c have to be 5. Okay, so there you go. That's kind of the new thing I wanted to touch on. Like if you're working backwards, the only way you don't have plus c is if you have an initial value. Okay. All right, then C and D are just kind of a review. When is the particle at rest? We know that is when v of t equals 0. So I'm just going to take my v of t equation and set that bad boy equal to 0. So I recommend pausing the video, trying that on your own, but it does factor to 2t minus 3 and t minus 1. So at t equals 3/2 and t equals 1, are we at rest? Okay. Okay, now if I were to, and this is purely just an extra part, like if I were to put that on another line, v of t, okay? It's at rest at 1 and 3/2. Like if I were to test some points here, like if I were to test, say 0 or something, that would be a negative times a negative is a positive. If I were to test like some number in between 1 and 1.5, you get a negative, and any number greater than 1.5 is a positive. So what this function is doing is it's moving forward, moving backwards, and moving forward. So let's talk about what happens if I want to know the distance traveled from 0 to 4. There's 2 ways you can do this. Okay? Well, really, I guess one way, if you want to think of it. We know the formula for distance is the integral, all right, from 0 to 4, of the absolute value of v of t. Okay? Absolute value because it's not displacement, it's distance. So we want to account for the negative and make sure it doesn't counter against our positive. Now, by hand, you need to split this up in the directions it's moving forward, backwards, and forward. You need to split it up and integrate it individually. Okay? All right, so we know that one break in the graph is at 1, absolute value of v of t dt. And we know that the other break in the graph, okay, is at 3/2. So that's from 1 to 3/2, absolute value of v of t dt. And then finally from 3/2 to 4, absolute value of v of t dt. So you'd integrate each of those pieces individually. Now the good thing is that we have already done the integration in part B. We know that the integral of velocity is position. So I'll write out kind of how this looks, but each of these pieces looks like this. The first part is the absolute value of s of 1 minus s of 0 plus the absolute value of s of 3/2 minus s of 1 plus the absolute value of s of 4 minus s of 3/2. And that could be doozy of a problem because it's a lot of plugging into this ugly position function over here. But it does end up being 14.75 feet. And I encourage you to, again, pause the video and try to do this step right here in the calculator to make sure you get it. And when we're together in class, I will show you how to do this in the calculator shorthand, where you don't have to write it all out. It is important to know how to do it by hand as well. All right, moving on. A little bit of review here. Determine the function being derived and the value of a. Okay. Number 2 goes back old school. This is the definition of a derivative. Definition of a derivative. See if you can try this one on your own first. Pause the video and try it. You're identifying the function and the value of a that's being derived at. Oh no, battery's running low. So just think back and write out the definition of a derivative. It's the limit, h approaches 0, of f of x plus h minus f of x all over h. Okay. So see if you can identify these pieces. I usually try to identify that piece right there, and I'm looking at that piece right there. So it looks to me like the function that's being derived is simply x to the 4th. Okay. And at what particular point? Well, that point is x equals 3. And you can take the derivative of x to the 4th and plug in 3, but all we were trying to do there was just determine the function of the value being derived. And just a little bit more clarification or a little bit more proof, 3 to the 4th power is 81, so we have that clarity there. And then lastly, in part 3, this is reviewing FTC part 1, right? Taking the derivative of an integral cancels it out. Well, remember, what happens is we plug the cosine function in for t, and then since it's something other than x, we multiply for chain rule. So 3 cosine x squared plus 4 cosine x, all of which is being multiplied by the derivative of the inside, which is negative sine of x. All right, there you go. That is our warm-up for the day. Pay at least close attention to part number 1. Okay. All right, now in today's lesson with the U substitution, just continuing, I have 4 examples I want to do with you. And we'll see, maybe we'll get through all of them. All right, this first one. Okay, the idea is, okay, so remember that the idea is to pick a U that's an inner function, Okay, and sometimes you might get it wrong. That's okay, right? But you gotta just go with it once you pick something. There's not much to choose from here. It looks like we have x plus 1 inside of a square root, so let's go with that. Okay. So then you get du equals, and then the derivative of x is just dx, and the derivative of 1 is 0. Okay. Now, the fact that we got du equals dx doesn't necessarily mean that we got it wrong. It just means that we might have to do something with it a little bit. So let's kind of see what I'm talking about here. All right, so I got the du equals dx, meaning I can plug du in for dx, and I can plug u in for x plus 1. So what I'm left with is x squared over the square root of u du. Now remember the goal of u substitution. The goal is to get it all in terms of u to make it a function I can integrate. Right now I still have an x involved. Okay, well, is there some way that I can substitute that x out, all right, with a u? Well, turns out I can. All right, what if I rewrite this as u minus 1 equals x? Could I not plug this in over here for x? So let's see what I'm left with. I got the integral of u minus 1 quantity squared over the square root of u du. Now, everything is in terms of u, and I should be able to integrate this a little bit nicer than the function up above. Got rid of that square root of x plus 1. Okay. All right, so now let's integrate this. Let's in order to do that, let's simplify the top and let's divide a little bit. I think we can simplify this. So right now we got u squared minus 2u plus 1 all over u to the 1/2. And since we're dividing by a monomial, we can just divide all the terms by u to the 1/2. And it simplifies down to u squared over u to the 1/2 is u to the 3/2 minus 2. And then u to the first over u to the 1/2 becomes u to the 1/2 power. And then lastly, we got 1 divided by u to the 1/2 is u to the negative 1/2. And now I got 3 power rules that I can simply take the integral of, right? U to the 3/2, if I add 1 power to that, that's 5/2. So we got 2/5 u to the 5/2 power minus 2. All right, if I add 1 to that, that's 3/2, and I divide, it's 2/3 u to the 3/2 power plus, if I add 1 to this is u to the positive 1/2 power, divide by 1/2 is 2, plus c. And then remember what we let u equal at the very beginning. All I have to do is just plug that back in for u, and I'm done. So this is just like the lesson from yesterday, except the fact that I had to do another little manipulation of my u equation at the beginning to finish substituting in at the beginning of the problem. That's 4/3 x plus 1 to the 3/2 plus 2 x plus 1 to the 1/2 plus c. There you go. Not too terrible. Let's try another one. Okay. So I got x plus 2 times the square root of x minus 2. I can't distribute anything. I can't really do any regular integrals. So let's do u sub by making an inner function, in this case, x minus 2, u. And if I take the derivative, I get du equals dx. So kind of not the best thing in the world, but I can plug in dx for du, and I can plug in u for x minus 2. So what I'm left with is square root of u du. Again, the goal is to get it all in terms of u to make this a little bit easier to integrate. Right now I still have this one little x left over. Just like before, I have an equation I can manipulate to get rid of that x. I can say that u plus 2 equals x and plug that in for x. So what I have is the integral of, instead of x, I have u plus 2 square root of u du. So I was able to do u substitution. I was able to get rid of all the x's by manipulating this u equation at the beginning. And now I can integrate this by just distributing and simplifying. Okay? This is the same thing as the integral of u plus 4 times u to the 1/2 power. And I can distribute the u. So I got the integral of u to the first times u to the 1/2 is u to the 3/2 plus 4u to the 1/2. Okay. And we can integrate that all day long. Okay, the add 1, that's 5/2, so we have 2/5 u to the 5/2 power plus 4 times, if I add 1, that is 2/3 u to the 3/2 power plus c. And then lastly, all you do is just plug back in whatever u is equal to, and you have your answer. There you go. Let's try a definite integral. These are always fun. Okay. Pause it, try it on your own. Pause it and try it on your own. I'm going to assume that you did. Did you let u be the inside of the square root? That looks like an inner function to me. So du is going to be 2x dx. And if you notice, we have the x dx right there. We have the x dx right there. So we just need to bring the 2 to the other side as a 1/2. Okay? So what I'm left with is 1/2 the integral of x dx has become du, and I'm left with 1 over the square root of u. And everything was in terms of u. All right? No need to have to manipulate this equation from the beginning, so that worked out good. The only other thing I like to do is, since we're doing a definite integral, I don't want to go back to x at all, so I'm going to put these bounds into u bounds by using my u equation. I'm going to say u equals the square root of 5 squared plus 4 to get my upper bound, which would just be 9. And I'm going to plug in the lower bound 0 for x to get my lower bound, which is 4. Okay. So I changed everything to u, the equation, the bounds, everything. So now I can just solve this out and never have to go back to x. We're set. So I'm going to ignore everything above that line. Let's go ahead and take the integral. All right, well, first of all, rewrite this as the integral of u to the negative 1/2 power and integrate that. So I'm going to add 1 to the power, which is positive 1/2, and divide. So I got 2u to the 1/2 power as my integral. Okay. And remember, that's multiplied by 1/2, and I'm evaluating from 4 to 9. Okay. Well, the good thing is that the 1/2 and the 2 cancel. So really, it's just going to be 9 to the 1/2 power, subtract 4 to the 1/2 power. I think that's going to work out really nice for us. It's just 3 minus 2, which is 1. So I highly recommend doing u bounds. I highly recommend putting everything in terms of u and not going back to x to get the same answer. Okie doke, and I only got one more problem, I believe. Yes, only one more problem. And we'll go ahead and do it. That way in class I can skim through this and we can just start on the worksheet. Okay. All right. We got cosine cubed times sine. U's got to be either sine or cosine. Let's just put it that way. Which one's an inner function though? It might help to write it this way. Right? Cosine cubed is the same thing as writing it that. So if you let u be cosine of t, good job. And du would then just be negative sine of t dt. Check it out. We got the sine of dt right here. We got the sine of dt right here. Let's just go ahead and bring the negative over and make sure we bring that out as a constant. And that can't substitute out. So we got the negative integral. All right, instead of cosine t, we got u to the third. Instead of sine of dt, we just got du. Again, not like the first couple examples. I don't have to manipulate the u equation at all. So we got everything already in terms of u. Now the only thing is like, since this is a definite integral, I don't want to go back to x. Practice putting this in u bounds. So if I have or I guess t, sorry. If I have an upper bound of pi over 2, the u bound that corresponds with that would be the cosine of pi over 2, which would just be 0. Okay. And the u bound for cosine of 0 would just be 1. So really this is going from 1 to 0. Now, a couple things. You could solve this out. You could integrate it, plug in 0, and subtract, plug in 1. But also, there's a little trick that can help us out just a little bit here. Since the upper bound is on bottom, you can actually switch this and change the sign. That would actually change this negative to a positive. If you don't like that, you can just solve it the way it is. But what if I switch this from 0 to 1 and change that to positive? Makes it just a little bit easier. And I don't have to go back up to x. I don't have to do anything above this line. I can just integrate and solve. The integral is 1/4 u to the 4th, evaluated from 0 to 1. So that's just 1/4, 1 to the 4th minus 0 to the 4th, which is simply 1/4. Okay. So I was able to do the warm-up and all the examples in under 30 minutes. Hopefully you pause the video and try a few of those problems. In class, we're just going to do a worksheet practicing this. We're just going to move right along. Okay, so hopefully you're doing good with u substitution. All right. Your homework's the worksheet. It's on Canvas. Go ahead and try it, and we'll talk in class. All right, guys. Thank y'all.